In this video, we will finish up our look at nucleophilic addition by enolates, focusing on intramolecular aldol reactions as well as considering other enolates that can add to aldehydes. So the aldol reaction involves having an enolate act as a nucleophile with an aldehyde which acts as the electrophile. Well, what if the nucleophile and electrophile are both in the same molecule? If we have this dialdehyde, for example, this is symmetric, so it doesn't matter which way we show this, but let's imagine that the hydroxide pulls off one of these alpha hydrogens, and that is going to lead to the formation of this enolate. So here we have our nucleophile and we have an electrophile. If this nucleophile shares its electrons with this electrophile, this is going to make a six-membered ring. And we know that six-membered rings are relatively stable, so this can happen. So we have our six-membered ring. Let's say this is the carbon that was the nucleophile. So this is still connected to the aldehyde, and it's connected to one hydrogen. And then that is connected to a CH2, 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 and then this is the O minus. Let's call this carbon 1, 2, 3, 4, 5, and 6. And so this is 1, 2, 3, 4, 5, and 6. So this can then grab off a proton from the solvent, and it would give us this aldol product. If this was carried out at elevated temperature, then it could do the aldol condensation, which would give us this product. What if we are looking at a diketone? I'm going to number this to begin with 1, 2, 3, 4, 5, 6, and 7. And so we have two alpha positions on the outside that are equivalent to each other, but different from two alpha positions that are internal and the same as each other, but different than the red ones. So hydroxide could potentially deprotonate one of the hydrogens at the red alpha position, and that would lead to this enolate. Or the base could deprotonate one of the protons at the green alpha position, and that would lead to this enolate. Let's look at the green one first. So if this nucleophile added to this electrophile, 1, 2, 3, 4, that's only 4 carbons away. So here we would be trying to form a 4-membered ring, and that is not easy. So that's not going to work. What about this one? Now this can add here, pushing these electrons up. I'm going to put these numbers back in again. We have 1, 2, 3, 4, 5, 6. So that is going to give us a new 6-membered ring, and let's call this one carbon 6, 5, 4, 3, 2, 1. So carbon 2 has the carbonyl. 3, 4, 5 are just CH2 groups. Carbon 6 is connected to a methyl group and to an O minus. And now this can grab off a proton from the solvent, giving us this product. Keep in mind, however, that because we are talking about nucleophilic addition to a ketone, that the position of this equilibrium lies toward the starting material. So if this was carried out under very mild conditions, so at low temperature, we would isolate only a very small amount of this product. However, if we heat this up just a little bit, then we can drive out water, and that would lead to this alpha beta unsaturated ketone in pretty good yield. So once again, we're losing a hydrogen from here and the OH from here to give the alkene at this position because this is conjugated. So just as we saw for intermolecular reactions, intramolecular aldol reactions can also occur. For addition to an aldehyde, the aldol addition product can happen, and with elevated temperature, the aldol condensation can occur. With nucleophilic addition to a ketone, the nucleophilic addition reaction is not favored, and so not much of that product would be isolated unless it's heated up to lead to the aldol condensation product. So far, we have looked at examples of having an aldehyde enolate add to an aldehyde, or a ketone enolate add to an aldehyde, and in both of those cases, because it's nucleophilic addition to an aldehyde, then this reaction should work pretty well. If we have a ketone enolate adding to a ketone, this reaction is not favored unless it goes all the way to the dehydration, so that we end up with the overall aldol condensation. What about other types of enolates? We've also seen examples where we can prepare an ester enolate. So if we have an ester and we treat this with base, then that base can grab off one of these protons, leading to the enolate. Plus the protonated version of the base, whatever that is. Now, a few different things can happen. We saw in the overview part of this chapter that this enolate could potentially add to the ester itself, and this would go back up, back down, and out, so we would be doing nucleophilic acyl substitution. And that could lead to some of this product. In the last chapter, we were talking about nucleophilic substitution, so we saw that we could potentially add, let's say, some methyl bromide, and then this could add here, kick out bromine as a leaving group, and we would do SN2 substitution, which would give us this. Well, it's also possible that if we had this ester enolate and we reacted it with an aldehyde, well, this nucleophile could add here, which would lead to, after protonation, I'm going to skip that step, we would end up with this. So, if we generate an ester enolate could potentially add to an aldehyde to do nucleophilic addition, which would result in the formation of a product like this. However, we have to keep in mind the other things that can happen. So, if we used a relatively strong base such as methoxide, then we would have some enolate but a lot of ester. Then it would be very likely that the ester enolate would react with the unreacted ester, leading to this condensation product. But if we used a much stronger base, such as LDA, then we could pull this equilibrium toward the products. That would minimize the self-addition, and then we could add in either the methyl bromide or any alkyl bromide if we're trying to do an SN2 reaction, or we can add in an aldehyde if we are trying to do nucleophilic addition. So this gives a lot of flexibility when it comes to different types of enolates acting as a nucleophile with different types of electrophiles. That makes it powerful in terms of the flexibility, but it can also make it challenging because there's a lot of possibilities. So it's important to organize the information about these different reactions so that you can tell what is going to happen.